Okay, so today we're going to talk about the product rule. So one feature of differentiation is that the differentiation is a linear operator, which means that if I have a sum or difference of two functions and I take their derivative, it turns out that you can just take the derivative of each component separately and add them together. I put up a more complex and general version of this rule, but this is the same rule and it holds true. But it turns out that this rule does not hold true for products. That is to say that if I have got two functions and I multiply them, I can't simply just take the derivative of one and multiply it by the derivative of the other. That doesn't work. Instead, we have to use something that's known as the product rule, which basically says that if you want to take the derivative of the product of two functions, you want to take the basically you differentiate each one of them, and you take the one of the functions and multiply it by the derivative of the other, and then you flip them. So then you take the derivative of the function that you originally just left as is, and then you take the derivative of the other function there. I know that's a little bit complicated to say. I think the easiest way to understand this is just to jump straight into an example. So suppose I want to take the derivative of this function here, okay? And we're going to use the product rule. So what we have is you'll see that we've got two functions here. We've got x cubed and we've got 3x squared minus 5. And those functions are being multiplied by each other. So the way in which we apply the product rule is we're going to take the original function here, x cubed, and then I am going to multiply it by the derivative of the second function. So this is like our u and this is our v. So the derivative of the second function here is just going to be 6x. And then I'm going to say plus, and then we're going to do the reverse. We're going to take the derivative of the x cubed here. And then we're going to, which is going to be 3x squared. And then we're going to just copy this second function down right here. Now, from here, we can simplify. So we can just use our regular algebra rules here. This is going to end up being 6x to the fourth. And then we need to make sure that we distribute this. So that's going to be 9x to the fourth minus 15x squared. And then we want to collect like terms. So this will end up being 15x to the fourth minus 15x squared when everything is all said and done. Now, when we do problems like this one that we just did, we could actually have done this whole problem without using the product rule by simply simplifying this function first by distributing this x cubed through. So if we do that, that's actually going to result. And again, we haven't taken a derivative yet, so we're simply going to leave this as d dx. And this is going to become 3x to the fifth. And then minus 5x cubed. And now we can just take the derivative term by term like we have in the last problems. So just like before, this is going to be 15x to the fourth minus 15x squared. So you'll notice that regardless of how you do this problem, you end up getting the same answer. Let's do one more example. Because in that last example that we did over here, you'll notice that you might ask yourself, well, what's the whole point of even doing a product rule or having it if you can simply just distribute like we did here? Well, there are some cases where you can't just distribute. For example, if you have a polynomial function multiplied by an exponential function, then you can't simply just distribute. So again, we're going to identify one of these as u, and then the other is v. And then it doesn't actually matter what order we do this in, just as long as you mix and match u prime with v and v prime with u. So in this particular example, I'm going to take the derivative of u first. And if we do that, we're going to get 2t. And then we're going to take the derivative of e to the t, which is just e to the power of t. So this leaves us with v and u prime. Now we're going to put a plus, and we're going to switch it. So instead of doing u prime, we're going to actually just put u itself, which is going to be t squared. And then we're going to put v prime, which will be e to the t. And then we'll just leave our answer like this. So one last example here is, well, what do you do when you have three particular factors, where you have something that looks like it could be a u, a v, and a w? Well, obviously in that case, you can't, the product rule works for two factors and not three, but this isn't really a big deal. What we can do is we can just associate a couple of these two together and call it u. So let's say this is u and this is v. Then we can apply the product rule. And the way in which we do this is when we find u prime, what we're going to do is we're actually going to do the product rule on just the first set of terms. We'll put it all in parentheses. So this is going to be 3x squared times e to the x plus x cubed times e to the x. And then we're just going to copy v. So v is going to be 4x squared plus 1. And then we can plug in u again. So u is going to be x cubed e to the x. And then v prime is just going to be 8x. Now, again, depending on the type of class you're taking, oftentimes, at least when I end up teaching a class like this, I don't really worry too much about simplification, because as you saw in the, not the last example, but the one before it, it might actually be easier to maybe distribute some stuff first. And in this case, it would be. But if the goal here is simply to get a derivative, without worrying too much about simplification, this allows us to do that. So that is it for this section. I hope you found this video helpful, and as always, take care.